So what are we doing in this video? It's just looking at general trends and seeing what kind of patterns we can develop with our graphs. First of all, we go back to the concept. If I have a graph of x sub t, that means if I want to get to velocity sub t, then I'm going to take the derivative of that to get velocity. So the derivative of displacement time is equal to velocity time. Now, if I want to get to acceleration time versus time, then I'm going to take the derivative of my velocity graph. Now, what about going backwards? To go from acceleration time back to velocity versus time, I must take the integral of that. To go from velocity time back to get the displacement, I must take the integral of that. So what does that mean, mathematically again in terms of the graph? So I've got a velocity versus time here. If I want to get the acceleration time graph, I'll say a sub t here. I would take the derivative of that. Okay, and that of course will equal some kind of constant value, but it's the slope. It is the slope of this graph. Okay, since we're a straight line, of course, that'd be a constant slope everywhere. But also remember, it's the slope of the tangent line drawn to the curve, but all of those would be the same value here. And I wanted to make this a simple graph for us to look at. Okay, now what if I wanted to, go backwards and get acceleration, or to get displacement versus time? Well, then I must take the area under the curve. Okay, now what I'm going to do there is think to myself, I've got a triangle right here. I'll just kind of like color in a little bit. And then let me draw some dashed lines here, assuming that I'm doing the entire interval here. And then I will do kind of like a coloring in of lines here, of course. So then we have a location right here. I'll just draw a dot there. This, of course, I'll just say is negative area 1. And we'll call this one here a positive area 2. So this just triangle, so 1/2 base times height, get the area of that. And 1/2 base times height to get the area of that. So that's going to equal then a1 negative, okay, plus a2. Of course, when you're doing this, on an actual equation, you can take, the derivatives of those equations and then plug in numbers. And if you're doing it on an integral, then you'll have a definite integral to plug in. But it is nice to know like if they tell you the beginning displacement, let's call it equals c1. And then maybe beginning velocity equals c2. It's nice that they give you the limits or the integral constants already. That way just in case they ask you, where is something located at the very end of the motion, you would need to know the beginning displacement. So this is kind of like the change in displacement. Okay, it's not actually the final location of the object. So once I do this area, okay, I would need then to consider what my beginning displacement was. So I can say, plus an x naught to get the actual location of my object. Okay, and vice versa. If I have a velocity time graph here, it's nice to know what my beginning velocity was, and then I can, figure out how fast actually it's going after a certain time interval. So that's how that's done. And finally, what about our graphing cues one more time? Well, if I have, we have two cases here that are very common in physics. I've got this concavity going this way. So we notice that we're, going downwards here and then coming back upwards here. Okay, I like to call that concave upwards. And this one here is upwards and going downwards. I like to call that concave downwards here. So if we were to look at the derivative of this particular graph here, we notice that we have a negative slopes here, then going to a 0 slope, and then back to a positive slope. Well, that would be represented by a velocity time graph that is a straight line going upwards like this. And then if we take the derivative of this graph, or slopes, then we see that there's a constant positive slope here. Okay, therefore you've got a flat line above the x-axis. In calculus, you would call this the second derivative test. This being the first derivative and that being the second derivative. Since I have a second derivative test where it's positive, therefore I must be concave upwards. Okay, now case 2, this one here is like free fall. You're starting positive initially, and then you're going to 0 and then starting negatively. So if I launch a ball upwards, it goes up to a max height and then back down again. So now we have positive slopes initially here going to 0 and then going to negative. That would be represented by this straight line going downwards. And then the slope of this line here would then give us a negative constant slope value here. So the second derivative test here is showing a negative value, okay, therefore concave downwards. And again, this is a great example of free fall motion where we have a constant negative acceleration due to gravity. So we can do our derivative test to determine what the actual constant acceleration is, pretty easily, and get a value in terms of what's happening with the motion.